So we're looking for a statement that's the same as this. All right, you guys already figured out that x would equal 4 in this case, right? Right?
Yeah.
Well, if I know that, I can just write 3 times 4 equals 12, right? It's a true statement, right? Or I could say erase that and replace that with a what's called y. This is also a true statement so long as y equals 12. Okay? We know these things, okay? I'm trying to remind you of what these things actually mean because now we're going to do the exact same thing but in a different context. Okay? Now, remember how I said that when we do matrices, we got these things, we got these things, and we got this line here, and we got like 1, 2, 3. I got that matrix, and maybe I have 5, 2, and 1. I said we have that line in there. I don't have to have that line in there. I don't. I can just have that. Now, what I showed you before, that is what we call an augmented matrix. Okay? Augmented meaning I got a matrix and it's augmented with a set of solutions. Okay? Now, I can get rid of that and I got just a matrix. Not augmented anymore. Meaning, now I'm going to erase this. Meaning, I got a matrix here, and then I can times it by something to get something. You feel me? So, in the case of the first page, going back to the first page, this is analogous to my 3. This is analogous to my 4. And we're going to find the 12. You feel me? But you need to know how I go about doing this. So the first thing I need to talk about is what does this 4 thing mean? What does this guy right here mean? Okay? This is a vector. Who's been in physics? Alex, you're in physics, right? Anybody else here in physics? Okay, but he's not now. We don't need to dime him out, right? Let's be kind. Okay, what is a vector though? You should know, right? Come on, smack talker. What's a vector? It's got size and direction, right? And I would say this has size and direction. How do I know this? So let's say this has got 3 numbers, right? Meaning it has 3 coordinates. It has an x, a y, and a z coordinate. Okay? Now if I drew this on a 3-dimensional graph, I'm going to have this is going to be my z-axis, this is going to be my x-axis, and then this is going to be my y-axis. So I go 1 over in the x direction, 2 over in the y direction, and up 3 in the z direction. So my vector is going to go from the origin to that point, which is 1, 2, 3. Okay, so this in red right here, that red dot is the point 1, 2, 3. Okay? Now this is kind of the first time that we've looked at this, but the logic should carry through, right? It should make sense to us. It's just a point in space, right? Instead of being a point on a plane, Zach, it's a point in a space now. I'm sitting at the origin, and I go over 1 in the x direction. I go over 2 in the y direction, and then I go up 3 in the z direction. So I'm just adding an extra dimension to my graph. Now, why haven't we done this at all in math up until now? What's that? It can be confusing, but is it really? Here's my proposition to answer that question. It's really hard to represent 3 dimensions on a piece of paper, right? Which is a 2-dimensional surface, right? So we stick with 2 dimensions because A, it's easier to put on paper, and B, it's easier for me to grade. This is 3 dimensions. We should have an intuitive feel for what 3 dimensions means. The power of this is this allows me to go to 4 dimensions. How big would x be if I was in 4 dimensions? It'd be another entry down here, right? How big would A be if I was in 4 dimensions? It would be another row down, but it would also be another column across, right? It'd be a 4 by 4 matrix. Okay? How many rows or columns would A be if I was sitting in 10 dimensions? 10 by 10. Okay? There's a lot of power in this. We're going to check it out in a hot minute. But first, I want to figure out what this means. Okay? I got this system, right? What does this line right here, 5, 4, negative 1, what does that represent? Yeah, 5x plus 4y minus z, and then I'm missing an equal something here, right? What does this column of values represent? It represents this point, which makes this vector, right? And at this point, what does x equal? 1. What does y equal? What does z equal? So what do you think I do with this guy and this guy?
Multiply their pairs.
This guy, the 1 in x gets multiplied by what in A? The 5. The 2 in x gets multiplied by the 4, and the 3 in x gets multiplied by the negative 1 in A. Okay? Here, and then I'm going to get an answer over here, right? I'll get an answer somewhere around here, okay? Now, what do I do with this 2? Remember, this is my, or I'm sorry, let me step back a second. What do I do with these values? That's what I meant to say. Same thing. This x times that. This times that. And this times that. And I'm going to get a new value I'm going to write over here. Lastly, this guy right here. I'm going to take this 3. I partially erased my 3. This 3, I'm going to take it and multiply it by this. I'm sorry, no. Step back. I'm going to take 1 and multiply it by this. Take 2, multiply it by this. And 3 and multiply it by this. And add them all together, right? And then I'm going to get a number right here. So let's do that real quick. I say real quick. So 1 times 5, 2 times 4, 5 plus 8 is, and then 3 times -1. 10, right? So then I get, I'll do this in red, 10. Again, 1 times 2, plus 2 times 2, plus 3 times 3. 2 plus 4 is 6, plus 9 is 15, yeah. Okay? Lastly, 1 times -1, plus 2 times 5. 10 minus 1 equals 9, plus 3 times 0.
9.
So then it's 9. Now, I got a new matrix. Or I'm sorry, a new vector. Now, here's the beauty of this. If I took, I want to take this guy out of the equation. Okay? And I want to take this guy, actually, that guy. Now I'll move it over here. Okay? And I have now I got an augmented matrix. If I did all the stuff that we did together yesterday to make this one, and this one, and everything else 0, what do you think my solution would be? Yeah, it would be this guy, right? So do you see how this is just the same thing as 3 times 4 equals 12, but in a different context? So there's great power to this. There's great power to this. Now, I am assigning this problem to you. I think it's number 82 in section 7.5. We're going to do something here. Everybody turn to page 539. This is your homework. I did not. You don't bring notebooks here. Page 539. Okay. Now, in problem 82 on page 539, it says, a company that manufactures boats has the following labor, hour, and wage requirements. Compute ST and interpret the result. Now S, what kind of matrix is S? How many rows and how many columns?
3 by 3.
It's a 3 by 3 matrix. We're going to put that stuff in there. Okay? S equals, and I'm going to put it in here. I'm going to leave the units out though, okay? So 1, 0.5, and 0.2. Is it a problem that I have non-integer values here? Actually, I'm not going to. I'm just going to make that a 1 because why have the 0.0, right? And then 0.2. And then lastly, it's 2.5, 2, and 0.4. What's the units on all these values here?
Hours.
Hours. So what do you think that means? So what's this matrix telling me? Amount of time for what?
Making a boat.
Yeah. So it tells me there's a lot of information here. First of all, it tells me how many hours it takes to make a boat, right? How many hours does it take to make a small boat?
1.7.
How'd you get that, Henry?
1 plus 0.5 plus 0.2.
Yeah. And how long do I spend cutting the pieces for a small boat? Right? How many hours do I spend cutting pieces for a medium boat? And somebody other than Henry, how about Zach? How many hours does it take to assemble a large boat? Do you have your book here? Okay. So this column represents cutting. This column represents assembly. And this column represents packaging. This row represents small. This row represents medium. And this row represents large. So it takes 2 hours to assemble a large boat. It takes 0.4 hours to package a large boat. Okay? So that's all the stuff. This stuff looks like things that might be in that spreadsheet thing that we looked at yesterday, right? You feel me? Now, I have T. T is another matrix. Oh, I boo-booed. I have T. And T is another matrix. What is the dimensions of this matrix? 2 by 2?
2 by 3.
Row by column.
Oh.
So 3 by 2. 3 by 2. And this is 12, 9, 6. 12, 9, 6, 10, 8, 5. Okay, and what are the units on all these?
Dollars.
They're dollars. Specifically, I think it said in the paragraph, it's the wage requirements. Okay, so now they want us to compute S and T. Now, let's go to another page. I'm going to go to a next page and you're going to read me, Henry, you like doing this stuff. You're going to read me the rows and I'm going to write them as you read them, okay?
1.
Hold on. 1.
0.5.
0.5.
0.2.
0.2.
1.6.
1.6. 1.
0.2.
0.2.
2.5.
2.5.
2.
2.
0.4.
0.4. Okay. So I got my S. Let me fix my brackets. And then T. What is 12?
10.
We on rows or columns?
Rows.
Okay.
9, 8.
9, 8.
6, 5.
6, 5. Okay. We're going to multiply S times T. Okay. So here's what I'm going to do. Oops. That's okay. That's okay. It's going to not let me do that, so I'm just going to do this. Okay? I'm going to multiply S times T. So, ST equals, and I'm going to multiply these two things together. Okay? So now, remember, this was plant A, and this is plant B, right? And what's this? Yeah. So this is the hourly wage for employees working a small boat, right? Oh, I'm sorry. Oh, cutting, assembly, and packaging. I'm sorry. So this is cutting, assembly, and packaging. These are all in dollars. So this is how much it costs for 1 hour cutting in plant A. This is how much it costs for 1 hour cutting in plant B. Assembly and packaging. Who gets paid the best in these plants? A plant gets the better pay. Which department gets the best pay? Cutting, right? You want to be a cutter in this company. You want to be a cutter in plant A in this company, right? So, I got wage, right? Now, here's the trick here. When I went, let's go back 2 pages. When I multiplied this, remember I took the A matrix, which is this stuff in black, right? And I multiplied it by X, which was a 3 by 1 matrix, right? This vector, how many rows does it have? It has 3 rows. How many columns? 1. 3 by 1 matrix, also called a vector. Okay? When I multiply a 3 by 3, that's A, right? A was 3 by 3 times a 3 by 1. There's 2 checks that I need to do to even know that multiplication by a matrix is possible. 1 check. These inside numbers need to match. So if these are the same, then I can do the multiplication. That's my first check. My second check is, what are the dimensions of my result going to be? And that is right here. It's going to be a 3 by 1 matrix that I get. And what did I get when I multiplied A times X? I got a 1, 2, 3 by 1 matrix. Okay? Now, let's go here. I'm multiplying a 3 by 3 by a 3 by 2. Yes? Can I do this?
Yes.
Yes, because these guys match. What dimension of matrix am I going to get? 3 by 2. 3 by 2. Okay? So I'll get a 3 by 2. I'm going to write that in blue down here. So let's write that in blue. Now, what we are going to do is we're going to just focus on column A for now. Column A. 12 times 1 plus 9 times 0.5 plus 6 times 0.2. Just like we did on the first problem, right? 12 times 1 is 12. Plus this and this is 4.5, so that's 16.5. And 6 times 0.2 is 6/5. So let's write that down as 12 plus 4.5, and 6/5 is 1.2. And we get 7, we get 7 and 1, 17.7. That goes right here. Okay? Now, I'm going to take column A again and multiply it by this row. 12 times 1.6. This eludes 19.2. Okay? 9 times 1. I can do that. 6 times 0.2, 1.2. That's 4. That's 19. That's 29. 29.4.
Wait, 22. What did he want?
What's 0.2 times 6? Right?
Oh, is that
12 times 1.6 plus 9 times 1 plus 6 times 0.2. I get 29.4. Now, the third one, 12 times 2.5. I can do that. That is 24. That's 30. So 30 plus 9 times 2, which is 18, and 6 times 0.4, that would be 2.4. 0, 50, 50.4. Now, what do you think this column that I just constructed represents? Go ahead. So it's cost after cutting. Well, is it the cost after cutting? Is this cutting, do you think?
No, it's the cost after production of one of those boats.
What kind of boat?
Small, medium, or large.
So the rows mean small, medium, or large, is what you're saying. Plant A is the column, right? That's plant A. Its cost $17.7 to cut a small boat. Not just to cut a small boat, but to assemble it and to package it, right? These are the wage requirements for a small boat at plant A. Okay? What do you think I'm going to get over here? What do you think that's going to represent? The same numbers for plant B. And this is going to be small, medium, and large. So let's compute the B numbers. 10 times 1 plus 8 times a half plus 5 times 2. 15, right? 0.2 times 5 is just 1, right? So 15. Ten times 1.6. Thank you. 8 times 1. 24. 5 times 0.2. So 25. And then lastly, 10 times 2.5.
25.
8 times 2.
30.
41.
40, what? Yeah.
16 plus 25, 41. And 5 times 0.4, 2, so 43, right? So, the columns are A and B, and the rows are small, medium, and large boats. So how much does it cost to make a medium boat in plant B?
$25.
$25. If you were a worker, where would you want to work? If you were a manager, what plant would you most like to cut? I don't want to cut plant A, right? Why? Cost the most. If I'm a manager, I want to cut costs, right? I want to cut plant A. So plant A, employees are enjoying it now, right? But will they for long? Maybe, maybe not. Take this. Whoa. Hey, how you doing? Doing well. What time do you think you'd be swinging in? 11 to noon. That should work. I'll either be in lunch or I'll be with my concepts algebra, which I am co-teaching with Kaz, so I'll be available for you, okay? All right, so just swing by my room. Bye. All right, so do we see what this represents? Okay? Spreadsheets are how business works. Spreadsheets and databases. Okay? This is just a formalized version of how we do math in business. Okay? But there's a lot of power in this that exceeds what we just do in business. We also use this in physics. We use it in chemistry. We use it in social sciences. We use it in economics. We use this in calculus. This will be Calc 4 for you. Calc 4, which is also called differential equations. You'll love differential equations. Guarantee it. Guarantee it. I got a D in differential equations. Ordinary differential equations. I got a D. Imagine how partial differential equations would have rolled for me. But partial differential equations also looks like these, except that tells you how heat dissipates. So what I can do, this matrix in partial differential equations might represent the temperature at every single position of a substance. And then I do some math to it to tell you what that temperature would look like 10 seconds from now. How the temperature would disperse through the material. Because if I got a hot spot in the middle of a sheet of paper, or a sheet of paper is probably bad. Let's say I have a cube of steel. We want to be fancy though, right? Let's make it tungsten, because tungsten sounds much more exotic than steel, right? And I got a hot spot right here in the top of that block of steel, or tungsten. I said tungsten, right? I got a hot spot right there. How is the temperature going to look, say, 5 minutes from now? You can say, well, you know what? Heat spreads, right? So the areas around it are going to get warmer, but that area in the middle will get colder, right? That makes sense, right? But what will the exact temperatures be? And this might be important when you're talking about stresses on a metal, when you're launching a space shuttle or something. It might be important, right? Because I want to know if my rocket's going to blow up.
Space shuttles are tired though.
Nobody likes a critic, Henry. But that's going to be important, right? And this stuff that we're learning right now, and we're just kind of going over a very informally, you're not going to get a summative on this or anything like that, but we see the use behind organizing our data in such a way, right? At least I hope so. At least I hope so. So that's what this is about, okay? That's how you do number 82. So if you took good notes, you'll have one of your problems done, okay? Another thing that I wanted to go over. Let's see now, page 521. 521 and number 56.
Copy is that page you're going to do a couple more.
56. Okay, that's number 56 on page 5, and actually this one's on 523. That one is the stuff that we did yesterday. You're going to have a 3x4 augmented matrix, and they're going to ask you to, well actually it's going to be a system of linear equations. They want you to convert it into a matrix and find the solution for this. And we did that yesterday, okay? And then these guys, we did 82. Okay. Now we're going to take a step back. And I want to show you how we can, let's say A equals 1, 2, 3, and 4. Okay? What's the dimensions of this matrix? 2 by 2. And let's call B 5, 6, 7, and 8. Dimensions of that. 2 by 2. Good. Now, I ask you, and I don't expect an answer. Well, give me a guess. But I don't expect a correct answer. But guesses are good. Do you think I can add these two together? So, what would the dimensions? Zach says yes. And that's a 50-50 question. So, it's a good chance that he's going to be right. And Alex even predicted my next question is, what is the dimensions of this matrix going to be? 2 by 2. So let's do that. Let's see if your intuition matches reality. What is going to be the result of A plus B? What do you think this number in the top left corner is going to be?
Almost 5.
So, 6. Okay. Good. Good, good, good. Now, how about 3A? What do you think 3a? Can I multiply? What am I doing when I say 3a?
A plus A plus A.
Yeah, I'm taking either a, the matrix A times 3, or I'm, like Henry said, A plus A plus A. 3 times. And what would that be?
3, 6, 9, 12.
So does Henry's intuition mesh with your intuition, Zach? What I mean is, did Henry take the words out of your mouth? Riley? Did Henry take the words out of your mouth?
Yeah.
Alex? Did Henry's word take the words out of your mouth? It's an idiom, Alex. It's not meant to be taken literally. Does your intuition meet up with his? Kristen? Intuition make sense? Okay. Now, if I wanted to do, let's do this in blue because I'm getting sick of the red. Let's do 2a plus 6b. How would I do that?
2, 4, 6, 8 plus 30, 36, 42, 48.
So Henry simply took 2 times that plus 6 times that. And then we come up with a what by what matrix? 2 by 2. Good. Okay. That is number 6 and number 14. Number 34, we get to multiply matrices. We kind of did that already, but these are all 2 by 2. So let's do a 2 by 2 times a 2 by 2. Let's do A times B. A times B. And it helps if I just write them together. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to do it just like we did the boat problem. 1 times 5 plus 2 times 7.
14.
5 plus 14 is 19, right? That goes here. Okay? Now, I'm going to do 1 times 6 plus 2 times 8. One times 6 plus 2 times 8. 16 plus 6, 24, right? Where do you think that goes? I have two different choices that might make sense to me. I can put it right here,
22.
or I can put it right here. 22, what did I say? Yeah, 22, you're right. But where, my question right now, where would I put it? Would I put it here, or would I put it here?
Okay.
Top right. Henry says top right. What do you think, Zach?
Yeah, sounds good to me.
Is that a guess, or are you really counting on Henry's?
I mean, Henry hasn't been wrong so far.
He hasn't been wrong yet. You ride the hot hand, right?
Yeah.
Henry's got the hot hand. What do you think, Alex?
Still not going to get happy.
What's that? That's the phone telling me that Mason was absent.
Where is he?
I don't know, but he's going to hear about it. So it's going to go up here, right? Because think about it this way. Everything came from this row, right? And everything came from this column. Top row, left-hand column. Top row, left-hand column, right here. And that was 22, Henry?
Yeah.
Okay, now we do it again, except this time we do 5 times 3 plus 7 times 4. 15 plus 28, that would be 33, 43? 43? 43 goes down here. And then 6 times 3 plus 8 times 4. So 18 plus 32, that'd be 50.
Okay.
And this is, you'll either see it saying AB, you might see A times B, or A x B. This one, very rare that you'll see that, because our favorite vector, remember a vector is a single column of numbers in whatever dimension we need. X with a little arrow above it like that is our favorite vector. Okay? Good. Good. Oh, I know what. So that's 34. Now let's go to another thing that we can do. Think about this. Remember how I said, let's do A again, which is 1, 2, 3, and 4. Okay? Remember how I said I could augment that with, pick a vector. A 2 by 1.
5, 7.
5 and 7. Remember how I said I could come up with a solution for this, right? How would I come up with a solution for this?
Well, we already have a 1, so taking the 4 1. And everything else 0.
Row 1 and row 2, right? So I would make this 0 and this 0, and then I would see what these numbers became, right?
Yeah.
So now, if I do that, what do I do to row 2 here?
Divide by 3.
Yeah, row 1 times -3 plus row 3. What do I get then? I still get 1, 2 up here and a 5 up here, but then I get 0. Let's see, this is -6 plus 4, right? So that'd be -2. And then I would get -15 plus 7, which being -8, right? So what does, and then, well, yeah, let's do that first. I like that idea. So let's do row 2 plus row 1.
No, because if we get this being a 1, we get a 1 in the x for row 2.
What's that?
You don't want that 0 to change.
So I'm going to do,
Oh, that's right.
I'm going to do row 1 plus row 2 to get a new row 1 now, right?
Yeah.
So when I do that, I get 1, 0, -3, right? And then I'm also going to divide this by what? Row 2, I'm going to divide by what? -2. So when I do that, I get 0, 1, 4, right? And here's my solution, right there. Okay? Now, here's what I would say. I could find an inverse matrix, an inverse of this matrix. Now, what does an inverse do? If I found an inverse to, let's call this matrix A right here. 1, 2, 3, 4 is matrix A. If I found an inverse to that matrix, what would that mean?
Went from 5, 7 back to 1, 2, 3, 4.
Well, it doesn't go back to 5, 7. Here's what an inverse does. So remember, what does this mean? This -3, comma 4. It means that when I multiply 1, 2, 3, 4 by -3 and 4, when I do that multiplication, what do I get? 5 and 7, right? That's what this means. Now, what I'm saying is that there's an inverse there's an inverse to that matrix, which I call A to the negative 1. And that inverse is going to undo what A does. So if I take A to the negative 1 and I multiply it by 5, 7, what should I get? Yeah, I'll get this. It's going to undo what A does. And we can find that. And here's how we do that. 1, 2, 3, 4. 1, 0, 0, 1. So I am going to augment this with what I call that matrix is called the identity matrix. Okay? What's special about this identity matrix? It's got ones in the main diagonal. This is the main diagonal. And then zeros everywhere else. Only square matrices can have inverses, and only square matrices can have identity matrices. Does that make sense? If I have a non-square matrix, is there an identity matrix to that? Well, no, because I'd have a 1 here, a 1 here. What would I have here? I don't know. So I can't do that. Okay? So basically what I'm going to do is I am going to augment A with an identity matrix. And then I am going to I'm going to turn this into an identity matrix and see what I get here. And this is going to be my inverse. And we'll test that. If we got time, we're running out of time, aren't we? Okay, so again, nice thing about this is I just did this. How do I make that a 0? How do I make that a 0? Negative 3 times row 1 plus that, right? So I'm going to stay 1, 2, 1, 0. Negative 3 times that plus that gets me 0. Negative 3 times 2 plus that is going to be negative 2, right? Negative 3 times that plus that. Negative 3 times that plus that. 1. Now, I can add row 2 to row 1 and give me a new row 1, right? So now, I got 1, 0, negative 2, 1. And I can divide this by 2, right? Or negative 2. And I get 0, 1, 3 halves, negative 1 half. And this is the inverse to A. And that will get you, let's see, 2. It will get you 12, 16, what's 16? 16, it'll get you 16, which is a riddle, and then 30, I'm going to have you refer to the formula on page 545 to solve that one. So all that's left is number 2. What do you think I get when I multiply A? A was 1, 2, 3, 4. What do you think I get when I multiply A by negative 2, 1, 3 halves, and negative 1 half? What do you think I get?
5, 7.
It's a 2 by 2 times a 2 by 2, right? I'm going to get another 2 by 2, right? What do you think that's going to be?
1.
The identity
1,
matrix.
0, 0, 1.
Yeah, let's check it. So the new matrix is going to be this let me get my eraser thing. This times this plus this times this, right? So 1 times negative 2 is negative 2 plus 2 times 3 halves. So negative 2 plus 3 is 1. Now, for this entry right here, 1 times 1 plus negative 1/2 times 2. Get 0, right? Okay, now for this entry right here, the bottom left, negative 2 times 3 is negative 6 plus 3/2 times 4, which is positive 6. Those cancel out, I get 0, right? Now it's the bottom row times the right-hand column. 1 times 3 is 3, plus 4 times negative 1/2, negative 2. 3 plus negative 2 is 1. So, question 2 asks you to see if A and B are inverses of each other by multiplying those two. So it's going to ask you, are A and B inverses? How do I find out? First of all, I check the dimensions. They have to be the same dimension, right? They have to be both square. And I multiply them, and I see what I get. If I get the identity matrix, then I know I have inverses. Does that make sense? That's your weekend's work.